Hey everyone, this is the Exam 3 review. So let me share my screen and we're going to just kind of review everything that we did since the second exam for the third exam. To begin with, we talked about the construction of the transducer and mainly three elements in the transducer. The first was the PZT crystals, or sometimes this is called the active element. Or you'll often hear it referred to as the active elements of the transducer. And of course, these work through the piezoelectric effect, and they send out the sound wave, right? And we'll talk in a moment again about how the frequency or the wavelength is determined. You should also know what the backing layer and the matching layer are for. Maybe I won't write them down here, but backing layer is meant to shorten the pulse, dampen the ringing of the crystal. The matching layer is to provide a uh, closer acoustic impedance to the crystal impedance so that more sound is actually transmitted out of the transducer. So we just talked about those basic elements. There are other elements that can be included. You might have a lens, for example, or something like that. Um, and again, the PZT crystals are all activated by a voltage, right? And sometimes I'll mention firing the crystals. And what I mean is a voltage pulse is sent to them to create the sound. All right, so let's go to the idea of central frequency and bandwidth. So when a pulse is created, there is a natural frequency that is emitted by the transducer. And we'll again look at a moment at how we determine that frequency again with crystal thickness. But the first thing I want you to remember is natural frequency. Anytime you hit something and a sound is produced, there is a natural frequency. And typically, larger objects will have a lower frequency than smaller objects. And this works, with crystals as well. Now, resonance is used to detect the sound, right? So I'm going to hit the crystals with a certain voltage pulse, a certain natural frequency of sound is going to be emitted. It's going to travel throughout the tissues and reflect. And when it comes back, it will also start the crystal ringing due to this resonance phenomenon, right? It's coming back with basically the same frequency as the natural frequency of the crystals. And so we can detect the sound that way through what we would call the inverse piezoelectric effect. Now, again, we need to know how crystal thickness and wavelength are related. And this goes back to our standing wave idea, although I probably won't ask about that on the test. But if you look at the thickness of the crystal, which I call T, and the kind of the longest or the first harmonic you could fit in there would look like our standing wave on a string, right, with one loop. Now, this is only half a wavelength, so it turns out that the thickness is equal to one half the wavelength of the sound. Now, of course, we want to convert this to frequency, and we do that using our good old V equals F lambda equation, right? And so if I just, again, solve for frequency, it's V over lambda, and I'm going to plug that into here. So my thickness I could write as one half times V, or sorry, uh, I actually want to solve for lambda here. So lambda is V over F. So I'm going to plug in V over F, the wavelength, and I could write this as V over 2F. So again, you can kind of see the size natural frequency relation. If I wanted a low frequency, I'd have to have a bigger thickness, right? A larger crystal. So this formula could be used in the problems. You might have a question similar to one of the homework problems where you have to calculate the frequency if you're given the thickness. Now, the speed that is used here is going to be the speed in the crystal, because that is where the sound wave is being generated. Pretty much all other speeds you will see will be 1540, the soft tissue speed, right? But in this particular case, we're talking about the crystal speed. All right, let's go on to bandwidth. So when you create a pulse of sound, you're kind of hitting it, ringing it, and then damping it. Right? So you're stopping it to create a short pulse. And what this does is introduce other frequencies into the sound. So you will get a central frequency, call it FC, but you'll also get a bandwidth. And the bandwidth goes, right, if you plot the amplitude, call it A here, versus the frequency, you got your central frequency here, but at half the amplitude, we have F1 and F2. And the difference between these is our bandwidth. So F2 minus F1 is our bandwidth here. Oh, there should be a minus sign. And in order to get a short bandwidth or a small or narrow bandwidth, you would have to have a long pulse. So continuous wave would have basically zero bandwidth, right? It would only have the central frequency. Whereas if you have a really, really short pulse, a small pulse duration, the bandwidth would be very wide. Okay. One way of measuring or representing the bandwidth and the central frequency is this Q factor or quality factor. Now, to begin with, let's talk about what we call fractional bandwidth. So the fractional bandwidth is just the bandwidth compared to the central frequency. So it's just going to be F2 minus F1 over FC, right? So it's just the bandwidth divided by the central frequency. Now the quality factor, QF, is just the inverse of that, 1 over the fractional bandwidth. So it's FC over F2 minus F1. So typically, if you have a small bandwidth, you're going to have a large quality factor. And so the question might be, does a pulsed wave have a higher Q factor when compared to continuous wave? And the answer would be no. Right? The biggest Q factor is going to be for continuous wave, because continuous wave, the pulse is a very long pulse duration, and you're going to have a very narrow bandwidth. Right? And so I think typically high Q factor would be relevant when you talk about continuous wave Doppler, for example. But it's just a number that sometimes is used to relate or talk about this idea of bandwidth. So with bandwidth, a couple things to remember, right? It's due to creating a short pulse. You have a wider bandwidth with a short pulse duration. The quality factor is large for a continuous wave and small for a pulsed wave. All right, so let's move on to our resolution stuff. And this should be elevational here. So we have kind of three spatial resolutions that are in space. So we need to remember our dimensions, right? So first of all, we had lateral, axial, and elevational. Now lateral is side to side. Axial is down the length of the beam. Elevational is up and down, right? And so I have some pictures in the other lectures that show representations of this, but keep those directions in mind. Also, you want to remember what the acronyms stand for, right? So I might ask a question where I ask, oh, which one of these is the same as the other, right? So if I ask, range resolution is the same as axial resolution, right? So lateral, or sorry, not lateral, longitudinal. So this is our axial. Now we could use range or radial are kind of used interchangeably here. And depth. So just remember that all of those words mean axial resolution. Now LADA or lateral can also be indicated by using azimuthal, transverse, or angular. So just remember all of those acronyms. Let me check here. So yeah, we'll go on to how we determine the resolutions here in a moment. Elevational really don't have another word for that, but it is the related to the slice thickness, right? The up and down slice thickness of the beam. And in fact, let's go ahead and define our resolutions. So axial or longitudinal lard is SPL over 2, right? So SPL is the pulse length in space, the spatial pulse length. So remember that this is related to pulse duration. In fact, we can write it as the speed of sound in the soft tissue times the pulse duration. So if I have a shorter pulse, I'm going to have better spatial resolution. Now, typically in an ultrasound system, right, sometimes what is done is you might have a certain frequency or wavelength, right? If you have a frequency, you have a certain wavelength, they're related. And you might introduce the number of cycles, n. So number of cycles. Now, if you keep the number of cycles the same, right, when you change the frequency, the wavelength is going to change. Typically, if you have a longer wavelength, you're going to have a longer SPL. So what this tells us is that a higher frequency that has a smaller wavelength is going to have a shorter SPL and better spatial resolution. So remember that a higher frequency means better axial resolution. And in fact, I think we saw this in the lab when we had the two transducers with the different frequencies. Okay, so for lateral, right, LADA, the width of the beam is what matters. And so one of the things we talked about here was where the resolution is the best is at the focal point of the beam, because that's where the beam is narrowest. So just remember, the width of the beam is what determines lateral resolution. And also to address what do I mean? So for example, if I had a lateral resolution, let's say of half a millimeter, 0.5 millimeters, what I mean by this is that the width of the beam is 0.5 millimeters at that place, and anything that's smaller than the 0.5 millimeters, I can't resolve, I can't see. Another way of thinking of it is that if I have two objects and they're any closer together than 0.5 millimeters, I will see them as one object, right? I can't resolve them. And that is true for all the resolutions. SPL, if I have two objects that are shorter or smaller than the SPL or closer together than the SPL, I cannot resolve them. Same thing with elevational, except now I'm talking about the slice thickness, right? I can't resolve them up and down. Now, in the image, what's going to happen, right? Well, in both lateral and axial resolution, LARD and LADA, you will see the objects blurred together. You can't tell the difference. It's kind of a little different with elevational. With elevational, you'll actually see both objects on the image. I just can't tell that one is in front of the other, right? Because when I take my slice on the screen, the computer compresses that into a two-dimensional image. And if both of those objects are in the slice, they get put in the same image, even though one is slightly behind the other. All right, so those are our definitions of resolution that we've talked about. Um, let's go and talk about our naturally focused beam. And as I said, the best lateral resolution, LADA, is at the focal point. Now, what about the near field and the far field? So remember that the beam shape is that it starts out narrowing a little bit, close to the transducer or close to the crystal, and then it gets to the focal point. And that's where I have the best resolution. So the resolution is getting a little bit better in the near field, right? Up until the focal point. In the far field, we start to get divergence of the beam. And as the beam gets wider, we get worse resolution. Now, the focal point itself depends on the diameter of the crystal and the frequency. And you might remember the formula for that we had. We called it the near zone length, right? And it was d squared times f over 4 times the speed, 4v. Now remember that the wavelength is v over f, so we could also write this as d squared over 4 lambda. And that formula could appear in a homework or, sorry, in a problem similar to one of the homework problems. Um, the other thing to remember is that at the focal point, what is the beam width, right? So beam width at the focal point, or at, well, yeah, well, at the focal zone, is 1/2 the diameter. So again, to summarize this, the near zone length depends on the diameter and the frequency. The higher frequency transducer will make the focal point deeper. A bigger diameter of a crystal will also make the focal point deeper. Now, we talked about there's a trade-off here. If I want a deeper focal point, well, I'll probably get more absorption because higher frequencies, we absorb more sound. And that trade-off could be asked about. I think there was a question in the lab about that. We also had questions about, okay, what is the lateral resolution at the focal point? Well, it's just equal to the beam width, which is 1/2 the diameter of the crystal. Okay, so up to now, when I say a naturally focused beam, I just mean I have a single crystal, for example. It sends out a beam, and the beam shape again is narrowing in the near zone to the focal point and then diverging in the far point. A couple other things to remember is that if I have a short focal length, I am going to get worse resolution in the far field because the beam is going to start diverging quickly and it will spread more. Okay, so that's our natural focus. There are several ways of changing the focal point apart from just having the crystal by itself, right? And so these focusing methods kind of uh, form into a couple different categories. One is fixed. So it means that I can't change this. I can't manipulate the focal point. I can have external means of doing this with an acoustic lens or an acoustic mirror, or I could have an internal one where actually in the transducer the crystals are curved, right? They are not like little rectangle shapes, they're actually curved. And that would change the focal point. And typically, the more curved the crystal, the shorter the focal point or shorter the near zone is. Now, there are also adjustable methods. One is an aperture. So I didn't really talk about this in the class, but you could have an actual opening that you make bigger or smaller. Now, the smaller the aperture, the smaller the hole that the sound goes through, the more it spreads and the deeper the focal length. Now, I'm probably not going to ask about that on the test, but that word does come back when we talk about segmental technology in a moment here. Now, the other adjustable methods are electronic or transmit, right? And this is our phasing technology, right? So you're going to send out pulses uh, at different times, and we'll come back to that again later. But you can create multiple focal zones this way in the beam that is sent out, right? Now it requires more lines, right? Because I've got to send out one beam and a second to get two focal points, for example. Uh, but it can be done by sending out electronically the timing of the pulses. There is another way that we won't talk about till next term. It's called dynamic or receive focusing. So this is after the sound has been received back, and this requires some mathematical manipulation that we'll talk a little bit about next term. So those are focusing methods. We have one other type of resolution, temporal resolution, and this is related to the frame time and the frame rate. In fact, I would say that what I mean by temporal resolution is the frame rate, right? The frame rate is the number of frames per second or number of images that can be produced by the machine every second. So the higher the frame rate, the better the temporal resolution. I can see things move more clearly in a continuous way the higher the frame rate is. And what is the relation between this? Well, remember, let's call it the frame time. I'll call it TF. It's 1 over the frame rate. Whoop. Or so it's just like a period and frequency relation, right? Frame rate is really kind of like the frequency of the images. So frame rate is 1 over the frame time. So you could be asked about this relationship. If an image is formed in 0.001 seconds, what is the frame rate? Just take 1 divided by 0.001. And typically we will, instead of saying, oh, it's hertz, we will say frames per second. It really is like a hertz, right? It's a thing repeating a certain number of times every second, but we would typically call it FPS, frames per second. So what are some factors that affect the frame rate? Well, one is the speed of sound in the medium, but we don't have control over that. And typically it's, the speed of the sound in the medium is pretty close, usually to the soft tissue, so it's not going to have a big effect anyway. The ones that we can kind of control are the imaging depth. Now, the deeper that you send out a beam, right, the longer the echo is going to take to come back. So that would increase my frame time and lower my frame rate. Now, the number of lines in the image. So typically when I talk about in a sequential technology way, what I'm doing is I'm sending out one beam, waiting, and then sending out another after the first one comes back. And I kind of go down the line. If I increase the number of lines, I'm going to have a lower frame rate. It's going to take more time for all those lines to go out and come back. And so, for example, if I went from 50 lines in an image to 100, my frame rate would go down by 1/2, right? Because there's that inverse relation between frame time and frame rate. Another thing that could affect the frame rate is multifocusing. Now, typically, if I do my transmit focusing, I might have to send out several pulses for every line, and that's going to take longer. So the frame time is bigger, frame rate goes down, right? And my temporal resolution goes down. Okay, so that's kind of a quick description or reminders about temporal resolution. One thing that was in one of the lectures that I forgot to talk about or answer was, well, let's compare these two systems. So we've got system 1 and system 2, and they have different characteristics. Let's ask which one has better axial resolution. Okay, so here I would go and I would look at spatial pulse length, right? I need spatial pulse length for this. Now, the only really thing that I have here that would affect that would be my cycles in my pulse and also the operational frequency, right? Because a higher frequency means a shorter wavelength. Now, I might look and say, oh, cycles in a pulse, that's going to give me broader thing. It also turns out this is a lower frequency, so it has a longer wavelength. So system 1 definitely has the worst axial resolution, right? It's going to have a longer SPL. So system 2 would be the answer for better axial. Which one scans deeper? Now this is asking about the frequency, right? The absorption is going to be higher for a higher frequency. So the 7 megahertz system 2 is going to absorb more quickly. That means 5 megahertz system 1 can scan deeper, which has a deeper natural focus. Okay, now this is going to depend on our frequency and our diameter, right? Now it doesn't depend on crystal width. Now, actually, I guess I should say it does depend on crystal width because this is the same as diameter. So I'm looking at this and I think, okay, well, first of all, the frequency might be a little deeper for the higher frequency one. Now this one also has a wider width though. Both of those things make a deeper focus. So I'm going to say system 2. Now which one has better resolution at the focal point? Okay, focal point resolution is 1/2 the diameter of the crystal. So the one with the smaller crystal width or diameter is going to be the better resolution, and that would be system 1. Better lateral resolution, the far field. Okay, well, in the far field, it's going to spread more with a shorter focal length. And so we talked about the one that has the deep focal length is system 2. System 1 has a shallower focal length, which means it's going to have more time to spread in the far field. So system 2, with its deeper natural focus, is going to give me better lateral resolution in the far field. Okay, lower Q factor. Now remember, Q factor is our 1 over our fractional bandwidth, FC over F2 minus F1. So it kind of depends on both these things, but typically I want to look at my bandwidth first. So F2 minus F1. So 11 minus 4, so that's 7. So I've got 7 for system 1 and only 5, 8 minus 3, right, for the bandwidth for system 2. Now it turns out the central frequency is 7 for system 2, which is higher than for system 1. Right, so it's got a higher central frequency, but the biggest thing is it has a narrower bandwidth. And we talked about more continuous wave it is, the higher the Q factor. So this is going to be system 2. Lastly, which has better temporal resolution? All right, let's go ahead and look at what gives us temporal resolution. Now, one of the things that is definitely going to do that is going to be our line density, right? So line density, we have more lines in the frame here, 200 per frame. That's going to take longer than system 2. So just looking at the line density, I'd say, oh, system 1 it's going to take longer. However, now look at the number of focal points, right? Number of focal points for system 2 is 4. That means I have 4 lines going out, or 4 pulses going out for every line. So if I want to actually get the number of actual lines or pulses that are sent out, I'd take 4 times 150, which is bigger than 200 times 1. So again, system 2 is going to have worse temporal resolution because it's taking longer, and system 1 has the better temporal resolution. Okay, so I went through that pretty quickly, but hopefully it's a good summary of how all the things are related. And if you do have questions, you can please bring them up in the lecture or in office hours. But we're going to go on to the last stuff that we talked about now. And this was our last lecture, kind of starting on last Wednesday and then ending on Friday. So we talked about ultrasound modes. First thing, know what these mean, right? So A mode is amplitude. B mode is our brightness. M mode is motion. And then Doppler, we kind of have 2 different modes. We have continuous wave and pulsed wave. So the other thing to remember here is kind of what they're doing. Amplitude mode, what is that? Well, it's a linear thing. It's one line, and it's plotting amplitude versus depth, right? So it's going to make just a graph. Now in brightness mode, you're really plotting amplitude versus brightness, with the higher, more brightness correlating to a stronger amplitude in the signal that comes back. And this is our basic 2-dimensional image mode. Instead of plotting some graphs, we're plotting brightness on the screen to indicate where we get strong reflections. Now, motion mode, we're going to plot depth versus time. And typically, with motion mode, so again, we're not getting an image, we're just going down one line and back, and we're getting the motion of all the structures on that line. And so they might move up and down closer or further from the transducer, right? Or you could say deeper, further away from the transducer. So just remember those basic characteristics. They could be asked about, what is this motion plotting, or what is it showing? For Doppler, know that continuous wave, right, is a single frequency. I can't form an image from continuous wave because I don't have the pulse going out to give me the time and depth information. Okay. Another thing to just remember, a continuous wave will deposit more energy, right? It'll give more sound exposure because it's constantly on, right? And that's going, back to maybe previous stuff, but it's something to remember. Okay. So lastly, we have transducer types and technology, and I haven't actually finished the transducer types. They will be in the lecture that we'll do on Monday. But basically, up to this point, we've talked about one-dimensional and two-dimensional, right? So we had, for example, the or sorry, the yeah, a single crystal transducer that sends out one beam. Now, sometimes you can form a two-dimensional image by moving the crystal, or you have two-dimensional arrays, right? So you have many crystals that are in an array, and those form the basis of our linear or curvilinear transducers. Now, we talked about several technologies. Sequential technology, we're firing the crystals in the array one at a time. We're waiting to receive the echo, and there is no focusing or steering here, right? Because you just got to wait for that to come back. The segmented technology, we have groups of crystals that get fired at a time. Now you can focus using that aperture focusing, because if I fire fewer crystals, it's kind of like a smaller hole that the sound is coming out of. It will spread more and the focus will be deeper. Now the phase technology, we're not going to wait for the echo to come all the way back. We're going to use small time delays in the firing of the crystals to either steer or focus the beam. So that's our phase technology. And I want to talk a little more about this, right? Electronic transmit focusing based on the phase technology. So if I want to steer, right, I can remember those pictures that we had, and I'll try to draw. We had a sort of a line with several crystals. We'll draw it this way. And let's say that I fire this crystal first, this one a little later, this one a little later, and I make a little slope like this. You should be able to see one of these pictures and know which way the beam is steered, right? It's going to be steered to the right, because this one is going to go a little bit further than this one and steer that way. So you might be given a picture of something like this. I have better pictures, of course, in the lecture slides, but know which way the beam is steered based on the pattern that each of the individual crystals is fired. Same goes for focusing. Let's say I want to use this transmit focusing. Well, what I might do is fire the crystals in a curved pattern. So I'm going to fire the outside ones first, the inner ones a little bit later, and so on. And it's going to be kind of a curved picture. And this is going to focus the beam. Right, and so I'll get my focus right here. Now, also know that the more curved the pattern is, the shorter the focal point. Now, lastly, I could focus and steer at the same time with this transmit phase technology. Now, how I would do that is I'd have sort of a curved, I'd fire this one, and kind of have a little bit of a curvature, right? But it's not going to be totally curved like this. It's also got a little bit of a slope to it. So it's going to kind of go to the right. Sorry, this one should be up a little higher maybe. But it's also going to focus over here. So I can steer and focus at the same time. So hopefully those pictures are clear. I think that covers everything that you could basically see on the test. So that's going to end the review here. Again, I'll try to leave some questions tomorrow for this.